So this is the first set of lectures for Base 2 in the summer semester of 2026, and I'm going to start by picking up where we left off in the previous semester. We ended with the most important chapter in the book, which was chapter 5. Of course, I covered base factors already, so that was chapter 13. But chapter 5 was really the important endpoint of base 1. So in base 2, we are going to start with chapter 6 and 7, which are about contrast coding. So let me introduce the idea. So let me just give you an idea of where we are going. So we're going to talk about the matrix formulation of the linear model. So just the standard linear model. And the reason we will do that is that this will lead us to the generalized matrix inverse, which is a very important mathematical object because that is the foundation for creating contrast coding, for doing hypothesis testing, or for estimating parameters that are theoretically interesting. So then I'll give you an example of a 2 by 2 factorial design where you can do this kind of contrast coding. Then we're going to talk about different kinds of contrast coding, starting with the simple 2-level factor, which you've already seen, right? So you've seen the 2 condition cases where you got some coding. That's a standard approach. But we also encountered treatment coding. If I recall correctly, we talked about treatment contrasts. So I will just review that material and talk about how these contrasts are set up and how they relate to hypotheses. Then we'll turn to a more interesting case of a 3-level factor, right? So, oops, sorry, I didn't mean to do that. So of a 3-level factor where we have one factor with 3 levels, for example, nouns, verbs, and adjectives. Maybe it's a production task or something. And so in that situation, what kind of comparisons can you carry out? So I will discuss that. And that will lead us to the this important idea of the hypothesis matrix and how we can use that to generate contrast. So we've got a package called Hyper that allows you to specify your hypotheses that you want to test. You can directly test those hypotheses, and the Hyper package then tells you what the contrast coding needs to be to test those hypotheses. So the big advantage of this is that you can pretty much specify your own custom hypotheses that you want to test. You're not tied down to treatment contrasts or some contrasts or whatever, right? So let me just switch on my light. Right, so I'll introduce the Hyper package, and then we'll talk about situations where you've got 4 levels of a factor, and there you can do treatment contrast, of course. There's also Helmut contrast, which we haven't seen yet, and I will also talk about sliding and sliding contrast, which are also called repeated differences or successive differences. And then we'll move on to chapter 7, which is about contrast coding for multifactorial designs, right? So 2 by 2 designs or 2 by 3 designs or whatever, right? And then one important idea there is to look at nested effects inside each factor level of one factor. If there's another factor that's crossed with it, you can check for the effects within each level of the factor, right? And that's pretty much it. That's the entire lecture, okay? So let's get started. Of course, as usual, the textbook is available for free. You can read the chapter, and you should read the chapter, of course. All the source code is all available too. And oh gosh, I made a mistake here. I'll just fix this. Okay, so this is the old chapter numbers before the publisher forced us to reduce the size of the book. So the chapters are just 6 and 7, not chapter 8. Okay, this has to be deleted. Okay, um, so to introduce the idea of contrast coding in general, one thing to know about the history of hypothesis testing is that the classical method for doing hypothesis testing in primarily in psychology but also in many other areas is, let's say you've got a factorial design. Okay, so let's say you have a 2 by 2 factorial design where you have two factors each with two levels. Now, how do you proceed with your hypothesis test? I'm talking about the classical frequentist approach. Okay, so how would I proceed? The traditional method for doing this is to carry out a so-called omnibus ANOVA, which checks if there are any differences at all between any of the factors, and it doesn't matter if it's a 2 by 3 factorial design or whatever. It just checks if there's any evidence for any main effect of each factor and of any interaction between the factors. Okay, and if there is evidence of a main effect and an interaction, the nature of that main effect and interaction will then be investigated further, okay, through pairwise t-test. So I'll illustrate this idea. Okay, so I'm going to take some fake data. This is data that's generated from in the BCOG-SCI package, right? Just like in Bayes 1. And so what we have here is a factor level, one factor, right, with 3 levels, so noun, verbs, and adjectives, okay? And there are some reading times or something, and it's a between subjects design, just for illustration. So these are subject IDs, okay? So a classic way to proceed now, suppose I have this kind of design, classic way to proceed would be to just carry out an ANOVA. So I'm using the RStatics library because I like the way they've set up the ANOVA there, right? So the omnibus ANOVA would work like this. It takes the data, right? And then it defines the dependent variable and defines the between or within factor level or levels. Okay, so in this case, there's only one between factor. So I say that in the data set DF contrast 2, there's a column called F that refers to the between subjects factor. And then once I've saved the result of that ANOVA test _test, I save it as omnibus ANOVA, and then I can get the ANOVA table from this saved object. And if I look at the results, what I get is an F score and a P score, right? What this is telling me is that, and the F score is referring to the F distribution, which has two parameters: numerator degrees of freedom, denominator degrees of freedom. If you don't know what that is, it's not really important because we're never going to use it, right? But if you want to know more, I discuss all this in my statistics course. In Stats 2, I teach all this, and it's also in my free online textbook for frequentist statistics. And of course, it's all there in textbooks, right? So you can find it. So anyway, like you get this F statistic, which is just like the T statistic. Actually, it's T squared. The T test. If you square the T value, you get the F score. So in any case, this is what this F score is telling me. It's telling me that there is evidence against the null hypothesis that there is no difference between the 3 levels of the factor. Well, that's not super informative, right? Like, I don't know what those differences are. All I know is that there is some difference between the 3 factor levels: noun, verbs, and adjectives. So what do I do now? I mean, I can now get excited and say, yeah, I have a significant effect, but I don't know what the nature of that significant effect is. So the conventional thing to do is to look at the 3 levels and do pairwise comparisons, compare nouns with verbs and verbs with adjectives, right? So of course you could compare nouns with adjectives, but if you have n factor levels, you can only do n-1 tests that are informative. The last test is uninformative. So all this is standard frequentist statistical theory, so like I don't really care about it right now. So we don't need to discuss why that is. But in any case, I've extracted the three, dependent variables, and now I'm gonna do like the two pairwise tests that I might be interested in, nouns versus adjectives. Remember, I'm doing a t-test that's not within subjects, so I'm not saying paired equal to true. This is a two sample t-test, right? And what I get is a significant t-value, blah blah blah, and so I can reject the null that there is no difference between nouns and adjectives. And if I do another test comparing, verbs with adjectives instead of nouns with adjectives, I again get a significant result, and so I'm all excited and I can publish my result. Okay, so that's the conventional approach. But the conventional approach actually doesn't make much sense. And psychologists noticed this back in the 70s. Like they pointed this out in textbooks. There's nothing new. Okay, there's not a new observation. But I don't know why, but history has just ignored the alternative approach. So this conventional method is redundant in the sense that why did I do the omnibus ANOVA when my real interest was in those pairwise comparisons? I should have just done those pairwise comparisons right away. So that's the whole point of contrast coding, right? You just go directly, once you've collected your data, you just go directly and compute the differences that you're theoretically interested in. Don't worry about the omnibus ANOVA because that doesn't give me any information anyway. The end result of such an experiment, would be focus on these pairwise results, right? Not on the omnibus ANOVA. The omnibus ANOVA is just used as a launching pad. So the logic is that if you don't get any significant effect in the omnibus ANOVA, right? So this, where was it? If the omnibus ANOVA had shown us a p-value larger than 0.05, then I would not do those pairwise t-tests. But I don't need to do the omnibus to check if there are the theoretically interesting comparisons are, if I have evidence against the null or not, right? So I would just directly do those. And so contrast coding in the linear modeling, in the linear mixed modeling framework, gives you that capability. It allows you to compare the contrasts of interest, the ones that you really care about. So, right. So now, in order to understand how contrast coding works, I just want to translate the standard linear model that we learned in chapters 3 and 4 and 5 to a matrix formulation, right? So the normal situation is that you've got some dependent variable, got some predictor x, and some parameter that is supposed to, predict, is telling us the relationship between y and x. Or you could have this more standard situation. You've got an intercept, which is the value of y when x is 0, right? And then you have the slope beta 1, which tells you the effect of 1 unit increase of x on y, right? This is what we studied last semester. So the interesting thing here is if you focus your mind on this equation, is that you can write it in matrix form, okay? And the matrix formulation is like this. So beta 0 plus beta 1 x is equal to y. I could just multiply beta 0 with 1 and beta 1 with x, and then I could just take the 1 and x out and put it in a row matrix, 1 row and 2 columns. And I could take the beta 0 and beta 1 and make it into a column matrix, right, with 2 rows and 1 column. So now I've got a 1 by 2 matrix, and here I've got a 2 by 1 matrix. And so if I were to multiply these two guys out, I mean, I assume that you know basic matrix operations. If you don't, just look it up, right? It's pretty straightforward. So basically what we do in matrix calculations is that the matrices that you're multiplying have to be conformable in that the number of columns of the first matrix has to be the same as the number of rows of the second matrix. Otherwise, you can't, by definition, you can't do matrix algebra. And so matrix multiplication, sorry. And then the way that you would do this is I would take this element 1 multiplied with beta 0, this element x, multiply it with beta 1 and sum those two products up. And that's what we have here, right? That's the end result of the matrix calculation. So that's why the translation works, okay? So I could more generally say that y is a function of x and beta, okay, where x and beta can be seen as, so beta is a now a vector of parameters, okay? And x could also be, would also be, generally speaking, a vector, okay, if we have more than one data point. So now the interesting thing is that this equation here, in statistics, in a statistical model, then this relationship between x and beta and y is not going to be exact, in the sense that once I know x and beta, I cannot exactly predict y, right? There will be some deviation between the observed value of y and the predicted value of y, given some estimates or even knowledge of beta 0 and beta 1, okay? So an example would be like, if I'm trying to predict height from weight, I could collect some data from a sample of people and then try to, estimate those two parameters, which I'll just talk about in a moment. I estimate those two parameters somehow, and now I've got a linear model that predicts height from weight, right? But what will happen is, for, let's say, weight, what is my weight? 57.4, okay? So I plug in 57.4, this model should predict my height, but it's not going to get my height exactly right? It's going to have some deviation, because there will be some random variation, right? So the problem we are facing now is that we have a non-deterministic version of this kind of deterministic model. This kind of model actually implies that if I know the if I know the weight, I can predict the height exactly, right? Which is obviously not true, right? So there's always going to be some error, some deviation between the prediction, right? And this is the deviation between the prediction and the actually observed y value, right? So actually y is now a function of three things, right? It's a function of x, beta, and that epsilon vector. All these are vectors now, right? Because we have multiple data points, presumably. So the epsilon vector is assumed to have some probability density function, and as you remember from the standard statistical stuff that we did in Bayes 1, normally the standard linear model assumes that epsilon is independent and identically distributed, coming from a normal distribution with mean 0 and some standard deviation sigma, right? So this is a non-deterministic function now, right? It's going to depend on what values of y and x you have, and what estimates of beta you have, and there will be some residual deviation around the predictions of the model given the data, okay? So we can now express this general linear modeling framework as a non-deterministic function, but what we can do is we can write it in matrix form now, right? So what I'm doing now is this is now, notice I'm using capital Y now, so this refers to now a vector with n rows and obviously one column, right? So it's a row matrix, right? So it's got n rows, one column, and so here this will be my predictor vector, and this will be my parameters, the vector of parameters in the model, and this will be a vector containing n residual terms, okay, because there are n data points, okay? So the matrix formulation of the linear model can be written like this: n is the number of data points, okay? And so what we are now doing, and then we have an index that ranges from 1 to n, okay? So what we are doing is, this capital Y is the observed data, X is the matrix now that contains this information. The first column is a 1 because that has to be multiplied with the intercept, and the predictor is another vector there. Okay, so that's my, this is my X matrix here, and this matrix will be how what will be the dimensions of this matrix? Because we have n data points, it will be n times p, where p is the number of parameters, right? And so this will be n times p, and beta will be p times 1. Okay, so we're going to get, when we multiply this matrix, we'll have n times 1, an n times 1 matrix. Okay, and this will be n times 1. Okay, so we are adding up n times 1 matrix with an n times 1 matrix, and we get as a result the y. Okay, so that's how this model works. You can write it row wise. Okay, so now here there's an identical statement here where instead of using capital Y, I'm using lowercase y, but I'm indexing each row in the data frame. This is important because when we start modeling data in Stan, we will actually write a for loop that defines how every row in the data frame is generated. Okay, so that's why I'm showing you this formulation. Okay, so now, so what does this matrix formulation look like? Well, it looks like this. So if you have only 3 data points, I have a 3 by 1 matrix here. I have a 3 by 2 matrix, which is my big X, capital X matrix. And this is my beta matrix, which contains the parameters, right? So you can see how this will play out now. This will give me 3 linear equations, actually. Right, so I'm writing them in a compact matrix form. And so what we generally do is we write it like this. Okay, all right. So one thing to remember is, I mean, people often mention this in standard linear modeling theory, that x beta is the expectation of y. So that's the expected value of y, because the expected value of epsilon is 0 by assumption, because it's got a mean of 0, right? So the expected value of y is x beta, right? So we write it like this, expectation, and the rest is, I think, clear. But what's important now is that this new term, X is the design matrix. It's also called the model matrix in R, okay? So if you fit a linear model in R, you can extract what's called the model dot matrix, but that's just the design matrix, okay? It's the same thing. And it has, as I said earlier, dimensions n times p, okay? So now I'm going to provide a geometric argument for how the beta parameters are estimated, okay? There are other ways to show how the beta parameters are estimated using calculus. So you'll see the derivations, you know, elsewhere. You can look it up in a stats textbook, in a mathematical statistics textbook or something. But I'm just going to give you a quick geometric argument for this, okay, about how these guys are, the beta parameters are estimated. So remember that, you know, in a standard algebraic setting, linear algebra setting, if we have a deterministic model, so y is a function of beta 0 plus beta 1x with no error term involved, right? That implies a perfect fit to all the data points, right? So this is like solving the ax plus b type of equation that you guys must have done at some point in your lives. So using Gaussian elimination or something tedious like that, you know, you can figure out what the b's are, right? So that's something that we know how to do. So literally, we are literally, you know, solving for beta in that kind of situation. So, but the problem is that we have a non-deterministic function, which is a function of 3 things: x, beta, and epsilon. So how do we proceed? Because there is no solution, right? So the best we can do is to get a solution that is as close an approximation as possible to b in this equation here, right? So we want to get ax to be as close as possible to b. That's the best we can do, right? So what we want to do is the absolute distance between b and ax needs to be minimized somehow. This is called the least squares approach to estimating the beta parameters. Okay, so the goal is to estimate the beta parameters here, and we want to find a value of the vector beta such that the observed y, the vector of data y, is as close to its expected value x beta as possible. Okay, so let's see how this works. Oh, by the way, here we are assuming that X is a full rank. Okay, that means the number of linearly independent columns or rows, right, are such that the rank, the number of linearly independent columns or rows is the minimum of m or n. M is the number of rows. Yeah, m is the number of rows and n is the number of columns. Sorry about that. I messed up this order. I should have put n times m. Anyway, so the X matrix has to be a full rank. Okay. So we have an X matrix in our design matrix, and it's also necessary that the number of data points, the number of rows in the design matrix, has to be larger than the number of parameters, larger than or equal to. You can't have like more parameters than the number of data points that you have. Okay, if you do have that situation, that model is over parameterized. Okay, so all this stuff is something you can look up in a standard, matrix algebra textbook, full rank and stuff like that. But we are assuming that X is a full rank, and we are assuming that n is larger than or equal to the number of parameters. All right. So in that situation, X is now full rank, and we have n larger than p actually in this setting. So in that situation, the vector of data, right, can be considered a vector in an n-dimensional space. Okay, so this is the vector y, and we have a subspace here that is x beta. So x beta here is referring to this entire subspace. So this will represent different values of beta, right? You could have any possible value of beta, right? So this subspace represents alternative values of beta. But what we want is a particular value for the vector beta such that the distance between the vector y and this subspace is minimized. So when will that distance be minimized? It will be minimized if we can minimize this distance, right? So like if I drew a line like this to this part of the subspace, I would not have the minimum distance. If I drew a line from here to here, I would not have the minimum distance. If I go vertically down at 90 degrees to the subspace, I have the minimum distance. Okay, so this is the least squares estimation approach, right? So the unique vector beta that corresponds to this point here, so which I'm calling x beta hat, okay, is the solution that we want because it minimizes the distance. So this difference here between y and x beta hat is the epsilon vector, okay, geometrically, right? So now, as I mentioned, the subspace x beta is perpendicular to epsilon, to this vector here, okay, and epsilon is equal to y minus x beta hat. So y minus x beta hat in brackets and x beta are perpendicular to each other. The dot product of two perpendicular vectors is 0. Standard matrix algebra, right? So we get the result that y minus x beta hat transformed to have conformable matrices times x beta is 0. right? Now if I multiply both sides, oh sorry, I divide both sides with beta, I get a simplification here, y minus x beta hat transformed times x is equal to 0. Okay, so now I'm going to use a result from matrix algebra that if you got two matrices A and B, which are in brackets, and then you get a transform on that, you can remove the brackets, but then you have to flip the two matrices. This is a standard result in matrix algebra. Okay, so AB transformed will become B transformed, A transformed. Okay, so here we have that same situation. Got y minus x beta hat transformed times x. So I'm going to open the brackets out here, and when I open the brackets out, I get y transform because there's just one term there. But here x beta hat becomes beta hat transform and x transform times. Of course, it remains in brackets because it's one unit, right? So I'm just changing this part here. So that's why I'm still retaining brackets outside the transform times x, okay? And that's also equal to 0. So that brings us to the situation that I can now post multiply this term. I can post multiply this term with x. So let's do that. So I get, when I open the brackets, I get y transform x minus beta hat transform x is equal to 0, which is the same thing as the next line because I'm adding beta hat transform x to both sides. So I end up with y transform x on the left hand side and beta hat transform x on the right hand side. Now, if I now transform both sides, I still get the same equation, right? So I'm going to change y transform x to, I'm going to change y transform x to y transform x transform, and I'm going to change beta transform x to the transform of that, okay? Now, opening the brackets out, I end up with reversing the two matrices, but a transform of a transform gives you back the original matrix, right? So y transform is y. That's why I end up with y here, okay? And x becomes x transform. So I have x transform y here. And similarly, if I open the brackets out, I get the flip of the matrices. This x becomes x transform. This x transform becomes x transform, which is x. And beta hat transform becomes beta hat. So this gives us a very important result that I can now solve for beta hat given the design matrix and the data. Okay. So how do I do that? I pre-multiply this term with x transform x, the inverse of x transform x. Okay. So if I pre-multiply both sides with the inverse of x transform x, I'm gonna wipe out this term here because any matrix multiplied by its inverse gives you the identity matrix. So I can just drop that, okay? So what I end up with is the very interesting result that I get beta hat on the right hand side, which I've just moved to the left hand side because it doesn't really matter, right? Because we really want to express the fact that we are solving for beta hat. And so I end up with x transform x inverse. So that was the pre-multiplication here, multiplied with x transform y. So this will allow us to compute the beta hats, right? Once we know two things, the design matrix and the observed data. That's how the solution works. That's how R also operates. It just does these matrix operations to compute parameters, the estimates of the parameters. Okay, so this is a very famous result and it's going to be super useful for us because this part here, everything before y, has a special name and it's called the generalized matrix inverse. And this generalized matrix inverse is a very, very important tool for us for contrast coding. And we can actually compute this inverse in the MAS library using ginf or in the MATLAB library using capital Ginf. Okay, so this is how these functions are implemented in in R for computing the generalized matrix inverse. So to give you an example now, right, how does this work? We have this data set. It's a 2x2 factorial design, and it's I think I have shown this data set before, but if I haven't, it doesn't matter. So in this data set, we have repeated measurements from multiple subjects who are being exposed to multiple items with a factor called distance that has two levels, short and long, and another factor called predictability, which I just shortened to predictability, which has two levels, predictable and unpredictable, right? So what I did here is that this is a very clunky piece of code. I should have done this better. I'm sorry about that. But basically, I'm just converting the four, unique levels, the four unique conditions, into alphabetical labels. So A, B, C, D, right? So what I've done is I've created a new column. If I have, let's say, short and predictable, all the rows which have short and predictable will be coded with some alphabetical letter, long and unpredictable with another unique alphabetical letter, and so on, right? That's what I've done here, okay? So what I'm doing is I'm mapping the condition levels to alphabetical values here, just for convenience, okay? So just like before, remember the sum coding that we did for two levels? So A and B refers now to, this is why I did it, because it's easier to write than to write short and predictable and long and unpredictable, etc. Right, so basically I could have just used the original labels, here for doing the sum coding, but it's just too tedious. In any case, so now conditions A and B refer to one level of the predictability factor, and conditions C and D to the other levels of the predictability factor, right? So the unpredictable cases. So basically what we've done here is that we have done sum coding for the two factor levels for predictability, sum coding for the two factor levels of distance, right? Same situation there. And then I just computed the interaction term by multiplying the two vectors, predictability and distance sum coded. I multiply those two guys, I get the interaction, which tells me the difference of differences. I can elaborate on that in the class if that's not obvious to all of you, okay? What I'm doing here. So what I'm doing now is I want to fit a linear model where I have three predictors: the main effect of predictability, the main effect of distance, all sum coded, of course, and the interaction, the difference between the two the difference of differences between the two factor levels, also sum coded, okay? So that's my setup. And for these data, for the Persian data, if I run the model, if I compute these parameters, I get an intercept, that's the beta 0 estimate, main effect estimate of predictability, of distance, and the interaction, right? Now I'm going to do this by hand using matrix algebra, okay? So first I use model.matrix from the fitted model, okay? I'm just extracting, I could have done this by hand, by the way. I'm just being lazy here. Just extracting the X matrix, capital X matrix is being extracted from the fitted model because it's there internally, that's how R does the calculations. So I get the X matrix. I have my data, which I've unfortunately written in lowercase, but it's actually supposed to be uppercase. So now what I'm going to do is I'm going to compute that X plus. What is X plus? Remember? Maybe I didn't actually write this down. I should have written this down. I'm sorry about that. But this generalized matrix inverse is referred to in statistics as the X plus matrix. Okay. Well, it's a pity I didn't really explain that in the notes, but I hope this is clear. Okay, so I will fix this in the notes. I need to write it down. Okay, so where was I? Yeah, so I'm going to do this calculation by hand. I have the capital X matrix, I have the data, and so I'm going to compute the X plus matrix. That's the generalized matrix inverse. Now solve in R will compute it for you by hand. So that means I'm taking the transform of X, matrix multiplying, this is the matrix multiplication sign, okay, with X, and then the that's the inverse. This is the inverse of the transform of X times X, okay? I'm multiplying that with the transform of X. Isn't that what the generalized matrix inverse was? Here, see? X transform X inverse, that's the solve function multiplied with the transform of X. That's what I'm doing here, okay? That's what I did. I'm calling it the X plus function because that's what it's called in textbooks. So the dimensions of this function are 4 and the number of data frames that I have, the number of data points I have, okay? Now, I'm just going to solve this function. I'm going to multiply X plus with matrix multiply X plus with the data Y. Why is that? Why am I doing that? Because of this. I've just computed X plus and I'm going to multiply it with Y and I'm going to get the estimates of beta, right? So let's do that. X plus matrix multiplied with the data gives us the beta hats. And if you look at the beta hats, these are exactly the numbers that I just computed with the LM function, right? So these are the, those are the actual LM function coefficients, and compared them with my hand calculated values for the intercept. They're all the same down to the last decimal point, okay? So conceptually, the contrast matrix can be represented in 2 different ways, so which I'm getting to in more detail soon. I'm going to talk more about the contrast matrix. So one representation defines the design or model matrix, right? That's the capital X matrix that I just mentioned. And it defines the independent variables in the linear regression model, right? This is the equation I started with today. And the other way to talk about the contrast matrix is in terms of the generalized matrix inverse, the X plus matrix, right? And what the X plus matrix does is that it defines the weights for how the observed data are combined to obtain estimated regression coefficients. So this is the equation just rewritten in terms of the generalized matrix inverse. And this is the equation that we're going to be, this X plus will be critical for us when we are defining contrast, as I will explain later, okay? But just to get a preview on this, now if we take the X plus matrix and we push it through the inverse, we invert that matrix. If we invert the matrix, which contains these weights for how the data are combined to obtain the estimates of the regression coefficients, what we end up with is the contrast coding that we laid out at the beginning of the data analysis, right? So we get back the contrast coding that we had set up. So the hypotheses that we are testing are actually encoded in this X plus matrix, and we can only see the actual contrast coding if we invert that matrix, okay? So we can flip back between the generalized matrix inverse and the contrast matrix using the design matrix, okay? Right. So basically, like mathematically, what's happening is that the generalized matrix inverse allows us to move from one space to another space, right? And that's all it does. And so it's a very important idea. There's more details on the generalized matrix inverse. If you're interested, you can look at the help in the MATLAB library on the capital G in function. Okay. The next topic that I will talk about is contrast coding. So maybe this is a good time for you to take a break. So the next part of this lecture is pretty straightforward because I'll be talking about two-level factors which you have seen repeatedly in base 1, and hopefully you remember the contrast codings that we encountered there, but I'll just quickly review this so that for completeness, so in case you've forgotten. So what we are doing here to demonstrate the use of treatment contrasts and sum contrasts is to set up some simulated data which is stored here in this data frame. And here what we have is one factor with two levels, f1 and f2. And this is all simulated data, and it sets up the situation that f1 has a true mean of 0.8 seconds and f2 has a true mean of 0.4 seconds. So there is clearly a difference between the two conditions, right? So we want to, when in a typical data analysis situation, when we have some such a factorial design, what we typically want to know is whether the difference between the two condition means is theoretically important or not. Okay, so that's the main goal usually. Whether you do a hypothesis test or whether you're just estimating the difference, in both cases you would still need to figure out the difference in the estimated means. So, and this is what it graphically looks like. So f1 has 0.8, f4 has 0.4, sorry, and so the difference is 0.4. Okay, we know what the true difference is here. Of course, so in this data set, because they are simulated data, we are getting exact means. When I compute the mean for f1 and f2, we are getting the exact means that are reflecting the true mean of the data generative process. But of course, that won't be the case in real life. There'll be some variation, of course, right? So the data set are only for demonstrating how one would do the analysis. So we set up a standard linear model, and we don't do any contrast coding. This f factor is treated as a factor, a type factor and not type character, right? Even if you set up the data frame to contain f as being of type character, BRMS will intelligently convert it to factor when doing this. I think that's true. Okay, we can check that. So anyway, we set up a standard linear model with a Gaussian likelihood, etc., and some reasonable priors. These are not really important here because I'm talking only about the contrast coding here. And so if you look at the result, the fit of the fixed effects, this is about 0.8 and this is minus 0.4, so the condition 2 has level 0.4, has a mean 0.4, and condition 1 has a mean 0.8. Therefore the difference between the two is given here as 0.4. So the difference between level f2 and f1 is minus 0.4, right? And of course these numbers are not exactly 0.8 and minus 0.4, and the reason for that is of course just this the problem with floating points in computers, right? So there's some variation there. But basically what we see is that the intercept reflects the level 1 mean, okay? The intercept reflects the estimate of the first level, f1, and the slope represents the difference between f2 and f1's estimated means, okay? This kind of contrast coding is the classical treatment contrast, right? So this is a very standard approach used in medicine because typically you've got a control condition and a treatment condition, and that's why it's called a treatment contrast, right? So the treatment condition is always coded 1, the control condition is coded 0. So it's pretty straightforward to see how the contrasts are set up. F1 is coded as 0, F2 is coded as 1, and the impact that it has on the equation is that when this predictor variable has value 0, what we have is the estimated mean of the first level, and the when this predictor variable has value 1, then we have the slope with the interpretation that it's whatever the F1 level's estimated mean is, the additional change that has to happen to that F1 level's mean to get the mean for F2. So it's really the difference between F2 and F1, right? That we're getting. So that's what's written here. And so you can see that yeah, right. So the intercept is telling you the level estimated mean for F1, and alpha plus beta hat is giving you the estimated mean for F2, right? So the slope itself is just the difference between the two means, right? And of course you could write this out differently. You could write -1 plus 1 as coefficients to the means of F1 and F2. So the difference between F2 and F1 would come out to be this quantity here, and that's why the slope is written, has the meaning that it's the difference between the two levels, right? So these are two equivalent ways to think about this. This will become relevant later on, okay? So I could write this equation like this, right? And it would still be the same statement. All right, so all this I've explained, I think, and I think this is pretty obvious that when F2 is coded as 0, we have the mean, or alpha representing the mean of F1 and so on, right? I don't think I need to belabor this point. The contrast coding I've already shown you. It's the level, so one level. So remember here, the default way in which the control condition is determined is that the two levels are ordered alphabetically, and the alphabetically first level is the control condition by default in R. Okay, well, you can change that if you don't like, if that's not the correct control condition, you can just flip the levels, with this kind of command. This one here, what I'm doing here is that I'm just taking the factor column and re-leveling the conditions. The order has been changed now. So whatever the first level is, that will be the control condition. And so you see that it's F2 is now the control condition. And what that will do is that the intercept will now represent the mean, estimated mean of F2, and the slope will represent the estimated difference between F1 and F2, right? So it'll have a positive slope this time, not a negative slope, because F1 has a higher mean, right? So if I fit the model again with the reversed, re-leveling of the factor levels, you'll see that the estimate for the intercept does change, because it represents the F2, the control conditions level, and then the additional number of seconds that you would have to add to the F1 level to get the F2 level, right? Sorry, to the additional seconds you would have to add to the F2 level to get the F1 level is 0.39. So therefore 0.4 plus 0.4 gives you 0.8, which is the F1 level's true mean, actually, right? So that was the treatment contrast coding. It's very convenient. Actually, you can use it for situations where you have more than one condition, more than two conditions, right? So you will have one control condition. You can have multiple treatment levels. So I'll discuss that example later. Okay. So then the next contrast, of course, you've seen many times, is the sum contrast, and typically we would set up the contrast coding as plus 0.5 minus 0.5, just like in base 1. And here we are explicitly setting up with the contrasts function. We are recoding we are overriding the treatment contrast coding by putting in the for f1 we are putting in zero point 0.5, and for minus 0.5, and for f2 it's plus 0.5. Right, so once you do that, what happens is that the meaning of the intercept of course changes. Now the intercept now represents the mean of the two conditions, okay, and the slope still represents the difference in the two means. So basically you'll notice that this number is pretty much the same as the very first model that I just fit, right? So the interesting thing here is that the intercept is usually of zero interest to us, right? We don't care what the average of the two conditions is in the sum coding. We don't care what the baseline conditions mean is usually, right? That's not, that hypothesis test is printed out in the LM function, and then and you can see all the estimates in the BRMS function, but usually the intercept is of no interest whatsoever. The only thing of interest is the slope or the slopes, right? And the interesting thing is that the sum contrast and the treatment contrast both give you the same interpretation for the slope, which is the really important thing, scientifically, I mean. So yeah, so this I've already explained, that there's plus 0.5 minus 0.5 coding, and once you know the alpha and beta values, right? This was very important in base 1 as well. Once you know the intercept, you have the intercept posterior and the slope posterior, you can figure out the estimates of each of the two conditions as well, right? In fact, in Bayes, what would happen is that this would be a vector of samples, this would be a vector of samples. So you could get a vector of samples that represents the mean of level 1 and represents the mean of level 2 in the same way. All that would change is the the contrast coding for that particular level, right? So that can be convenient, although I just said that we are never interested in each conditions mean, but in the Bayesian setting in particular, if you get these vectors, you know, based on these posteriors, alpha and beta head, you could just take the difference of those two vectors. You get the posterior distribution of the difference between the two conditions. That's very convenient, right? So I mentioned that because sometimes people code the do the sum coding with +1 -1. So it doesn't really matter, you know, whether we code it plus 0.5 minus 0.5. We can still derive the estimates of the two, you know, the two levels, and we can work with that and figure out, we can always figure out the difference between the two means, right? Okay, so I think I've explained all this now. There's not much to say here. One important thing to notice is that you should keep this in mind in case you find yourself confused at one point. This grand mean that is represented in the sum contrast in the intercept, the grand mean the estimate of the grand mean that you're getting will represent the mean of the two conditions only when the data are balanced, if you don't have any missing data. In real life, that is rarely the case, okay? So what will happen is, if you have any imbalance in the data, this estimate will not exactly represent the difference between the two means. It'll be a weighted average, right? Because if there's some missing data, then the average calculation will be the calculation of the average will be a weighted mean, right? So this is explained here. Is it, sorry? Did I? Yeah, here, sorry, I wanted to demonstrate, just quickly illustrate this point. When you have missing values, right, you'll get the intercept will not represent exactly the the average of the two conditions, right? So suppose you have fully balanced data and two equal group sizes of 5 subjects for each group, F1 and F2, then the grand mean is also going to be the mean across all subjects, right? Because if you were to take the entire vector of dependent variables, compute the grand mean, that would be the the same number as the mean you would get for computing F1's mean separately, F2's mean separately, and taking the average of those two, right? The average of the averages is going to be the same thing as taking the average of the whole vector. That's in the balanced case. But suppose you have a unbalanced design where in condition F1 there are only two observations, right, with the values 2 and 3, and in condition F2 there's only one observation, right, with a value of 4. So in this case 2 plus 3 plus 4 divided by 3, right, that would be the grand mean of the entire vector would be 3. But if you take the weighted grand mean as assessed in the intercept in the model using some contrast coding, what that would amount to is first computing the mean of F1, that is 2 plus 3 divided by 2 is 2.5, and the mean for F2, there's only one data point, so the mean of F2 is 4, and therefore we've got 2.5 and 4. Now if we take the mean of these two guys, 2.5 and 4 divided by 2, we get 3.25. So we're not going to have the same value as the grand mean of the entire vector. Okay. So the important insight here is that treatment contrast and some contrasts give you the same information in the slope, but the intercept is different, and you have to pay attention to how you're parameterizing your model, right? Because that can affect the meaning of the intercept and slope parameters. That is very important. The meaning of these two parameters is very important for us as Bayesians because we're going to decide on the priors. Now, deciding on the prior for an intercept that represents the grand mean can be a very different decision process than deciding on a prior for an intercept that represents the baseline level of the factor, right? So you have to be careful about that. Of course, if you have uninformative priors, it's really not going to matter much, right? But in some situations, you will be able to have reasonably informative priors. And as I showed you in the reading time data with the log normal likelihood in chapters, I don't know, 3, 4, and 5, we were using 6 or so as the mean of the intercept on the log scale, right? That's a reasonably informative prior. But the reason we do that is we want a reasonable prior predictive distribution, right? So if you care about producing or creating a model that is a priori reasonable, then you wouldn't be using uninformative priors because then you get wild prior predictive distributions, right? And it could also influence your posterior, depending on how much data you have, right? And so what we're going to talk about next, in the next topic I will discuss, is how we can work with more than 2 levels, and I will discuss the concept of the hypothesis matrix. Right, so until now, what we've been discussing is pretty much standard stuff. You must have encountered it in Bayes 1 and in any matrix algebra class that you might have taken. So none of the material until now has been new, and so you might be wondering what's the big deal of all this contrast coding. The big deal is that we can now define any contrast that we want to specify. And why is that a big deal? It's a big deal because when you're working on a research problem, you don't necessarily have the canned, you don't have hypotheses that match the canned contrasts that are available to you by default, like treatment contrasts and some contrasts. You might have a custom contrast that you want to define. And the big deal with this whole setup with the design matrix and the generalized matrix inverse is that we can actually define the hypothesis that we need to get an answer to, right? So the hypothesis matrix or the comparison matrix, maybe you can call it, is the key idea here. Okay, so we're going to illustrate this with a 3-level factor. So this is also simulated data also from the package BCOGSAT. We have nouns, verbs, and adjectives, and some dependent variable like reading time or something, and you have some subjects data. So each subject is delivering one data point here. So it's a between subjects design, just for simplicity, because none of the machinery here really depends on there being a within or between subjects design. It's just simple linear modeling. So we just chose the simplest possible setup. So now if you look at what the number of data points are for each of the 3 categories, adjectives, nouns, and verbs, we have 4 data points each because it's just a toy data set. And the mean is given here with standard deviation, etc. Right? So if you see, adjectives have 400.25 as the mean, nouns have 500, and verbs have 450. Okay, so for example, if I wanted to compare adjectives and nouns, the difference between them would be about 100 milliseconds. If I want to compare nouns and verbs, the difference between them would be 50 milliseconds, right? Roughly speaking. So in any case, the interesting thing here is the idea of a custom contrast. Okay, so it could be that you are interested in knowing whether the nouns are the response times or reading times for the nouns are different from the grand mean, and by how much. And do the adjectives also differ from the grand mean? So mu1 refers to the nouns mean, and mu2 refers to the adjectives mean. And right, that's what it refers to. And the research questions that we have are not definable using any built-in contrast in R, right? So what we want to know is whether the first level's mean is different from the grand mean, so the mean of all the 3 conditions. And the second question that we have is the second level of the condition, whatever it is different from the grand mean, right? So you could write this. So the slopes in our model should represent these comparisons, these contrasts. Okay. So one interesting thing to notice is that, for example, just consider the very first equation, 24, right? I could rewrite this equation by just removing the fraction part, right? So what I would do is, if I were to open out this this term, I would get mu1 equal to 2/3. Why? Because it would be mu1 times 3 divided by 3, and then if I break up this into 3 terms, then I would have 3 times mu1 divided by 3 minus 1 times mu1 divided by 3. That gives me a 2/3 mu1. And similarly for the others, I would end up with minus 1/3 mu2 and minus 1/3 mu3. So the condition we want to compare to the grand mean ends up getting a weight. This is a weighting now of 2/3, and the other guys get a weighting of minus 1/3. Okay. Similarly, for mu2 gets a weighting of 2/3, and the other 2 get a weighting of 1/3. Okay. So for the 2 comparisons we are interested in, the weightings that we have, the weights that we have are 2/3, -1/3, -1/3 for the first one, and -1/3, 2/3, and -1/3 for the second one, right? So what is this good for? Okay. What we've done so far is we've been defining the parameters in terms of mu1, mu2, mu3 by giving the three mu's different weights, and by giving them different weightings, we are defining a particular comparison. Okay, so um, we are now going to generate the contrasts that we need in the linear model that represent those weightings, those comparisons, right? Why is that good? That's good because now if we want to do a hypothesis test, we can simply do the hypothesis test on the slopes and we get the answers to the question. If we're interested in estimating those parameters, let's say I'm anti-Bayes factors or something, right? And I just want to be able to get my posterior distributions and that's it. There are people like that. Andrew Gelman, for example, right? They don't like to do Bayes factors. They just want to know what the estimates are. You can do that too. So that's why I said you could call it a hypothesis matrix or a comparison matrix if you're not into hypothesis testing. The reason it's called the hypothesis matrix in statistics is that this whole theory was developed within the frequentist framework, and the frequentists are always doing hypothesis testing, right? So the weights that I just showed you, these weights that I showed you, these are basically intended to give us a contrast matrix that allows us to do hypothesis tests in the frequentist setting, right? But it's a more general thing, right? You can use it just to figure out the posteriors of the comparisons of interest. So the approach we're going to take is the following. We write down the comparisons formally. I just did that, right? So those two comparisons. Then extract the weights. We did that too, of the condition means from the comparisons. That was -1/3, 2/3, -1/3 for the first one, and then 2/3, -1/3, -1/3 for the second one, right? And what we're going to do with those weights is that we're going to generate a contrast matrix that we need to estimate the comparisons in a linear model. So we're going to use the contrast matrix in the linear model. We're not going to use these weights. These weights are just an intermediate stepping stone that gets us to the contrast matrix. All right, so the advantage of this is that we are no longer tied into the contra sum, contra treatment, etc. functions that are available in R. We just define our own contrasts, right? All right, so let's do this. These are just the same methods as earlier. Once we extract the weights and write them down in a matrix, which I'll call the hypothesis matrix, and once we have that hypothesis matrix, which contains the weights of the comparisons, you apply the generalized matrix inverse, using the ginf function to the hypothesis matrix, and what that gives you is the contrast matrix. That's what goes into the linear model for the comparisons. Okay. And then we just assign that contrast matrix to the factor levels, right? And then run the model, frequentist or Bayesian, doesn't matter. Okay. So then we get to the hypothesis matrix now. I'm going to show you how this goes. So let's go. We know the weights, right? The two weights are here. So here's my first. Here's my first set of weights, right? Adjectives compared to the average of the others, right? That was the weighting. And this is the second set of weights, so I might have mixed up the category levels. So here we are comparing the nouns against the grand mean, and here we are comparing the adjectives against the grand mean, right? And this one here, this row here is just going to test whether the grand mean is different from 0. That's the intercept again. Okay, so our three hypotheses now. This one is the hypothesis that will go into the intercept, And these are the two hypotheses that we actually care about. So the slopes in the linear model, right? So these are the weights that we got from our comparisons that we set up. And we've just rearranged, by transforming the matrix by using this T function, we just transformed it. So it's easier to see the three hypotheses, relative to the three levels of the factors. So now let's use the ginv function. So there's just some prettification going on in this function that inverts the hypothesis matrix. Okay, this HC sum is going to get inverted now using ginv, and when we do that, what we get, here's the fancy cleaning up function. This function is just a cleaning up function, just makes the output look nicer. Okay, so you can look at the details. But now I've passed the hypothesis matrix through the generalized inverse, and I get back the contrasts that are interesting for me, right? That represent the hypotheses. This HO1 and HO2 are the contrasts that I need. So these are the sum contrasts I'm going to be using now in my linear model, right? So when I want to compare for the first slope, right, the predictor variable will be coded 1 for adjectives, 0 for nouns, and -1 for verbs. Similarly, the second slope will have a predictor, vector that will be coded 0 for adjectives, 1 for nouns, and -1 for verbs, right? So all the levels that are coded -1, and this is of course the intercept, right? All the levels the level that is coded -1 is never going to be involved in the hypothesis testing or the derivation of the slopes. Okay, that's it's set up to be -1 here. What I mean is that that's what the -1 can be interpreted as. Okay. The condition that will be compared to the grand mean is coded as +1. So that's this one, this one. I'm only talking about this part here. That's just the intercept. Okay. So now the interesting insight here is that if you don't know what the hypothesis matrix is, then you can't, by just looking at the contrast matrix. If you look at this, if I asked you just out of the blue, if I asked you what are these comparisons, what do they mean? You may not be able to tell me. And in fact, I wouldn't know if I hadn't studied this stuff, okay? As a user of statistics, if somebody threw these contrasts at me and tell me what they mean, I would have no idea, okay? So I'm talking 10, 15 years ago, okay? Or not even 10, 15 years ago, I don't know, like maybe 8, 9 years ago, okay? So, so the interesting thing is that if you know what the contrast matrix is, you can figure out what the hypothesis matrix is by inverting it. You invert the contrast matrix, you get back the hypothesis matrix, and that tells you what the weights are. And those weights tell you what the comparisons are that you're doing. So this relationship is not necessarily obvious. Not in every case. In some cases it is obvious, okay? But not in every case. And so that's why it's so important to understand the relationship between the hypothesis matrix and the contrast matrix. It's kind of amazing to me that like nobody ever taught me this stuff. It's kind of shocking, right? Because like this is such an important detail. And I studied statistics at Ohio State and like nothing, So it's really makes me very angry actually that it took me so long to figure all this stuff out. Okay, so sorry about the rant, but it's just an amazing detail, that gives you so much power now because you can decide on whatever your hypotheses are going to be, right? It's up to you. So like if you look at we can demonstrate, that if you take a contrast matrix, if we invert it, we're going to get back the hypothesis matrix. So here's a contrast matrix. Contrast sum 3 is going to do the sum coding for the, 3-level factor that we are interested in. And here just the intercept has been added, that's all, because contrast sum doesn't add intercept, okay? And so if you invert, no, so if you look at the contrast matrix, that contrast matrix that you get, it's exactly the same thing as this guy here, right? It's the generalized inverse of the hypothesis matrix. And if you were to invert the contrast matrix, you'd get back the hypothesis matrix, okay? So once you figured out what the, contrast matrix is, we're going to assign those to the factor levels. So this time we drop the intercept column. Okay, we are dropping this column because the contrasts sound only about the comparisons of interest, which is the slopes. The intercept is automatically added by R. You see, this, even if you don't write that 1 plus, the intercept is going to be there by default. So the ones will be added automatically. So for the contrast, using the contrast function like before, I can plug in my contrast matrix into the factor specification and get back the comparisons I'm interested in. So that's what we're doing here. And so if you look at this, right, the intercept is representing the grand mean. You can go and check if that's what it represents. And the first comparison compares whatever the level was, I'm sorry, I forgot now, with the grand mean, and the second one compares the whatever the interesting level was with the grand mean. You can check that later if you want, right, with the data. And the numbers here will be roughly the same. They'll be like 50 or minus 50 or something, but they're pretty close to 50, right? So so that's the really interesting part of the hypothesis matrix. It gives you the ability to choose your comparisons, right? Okay, so that's pretty much it for the hypothesis matrix. The next topic I will cover is the hyper package, how to use it, and how it allows you to transparently define your hypotheses and extract the contrast matrix, which you can plug into your factor and override the default coding of treatment contrast, and go ahead and just carry out the comparisons that you actually care about instead of doing some kind of omnibus ANOVA first or something. So that'll be the next part of this lecture. So now I'm going to talk about section 4.8, which involves using the hyper package for first defining the hypotheses that you want to test or the estimates that you want to get from your model, and then extracting the contrast codings that you need to put into the model to test those hypotheses or to get those estimates, right? So let's try out some examples, right? So suppose that let's say we have 3 conditions, and one of our hypotheses is that the mean of the first condition is different from the mean of the other mean of all the conditions, so the grand mean. Okay, so is the difference between the mean of the first condition and the grand mean different or not? So the null hypothesis would be that this difference is 0, right? So that would be one null hypothesis. Another one could be, so these are just examples, that the mean of the second condition is different from the grand mean. So the null hypothesis would be that the mean of the second condition is the same as the grand mean. So I've just written those things out now for the 3 conditions here, right? So So basically, whenever you do comparisons or hypothesis tests, you're always comparing one condition or a bundle of conditions against a bundle of other conditions, right? And so this is an example of that. So using the hyper package, if you're talking about the adjectives, nouns, and verbs example with the three conditions, so we could have one hypothesis that the adjectives are no different in whatever the dependent variable is um, than the grand mean of the reaction time or whatever, right? So this is the grand mean of the reaction time. So I'm literally writing out the hypothesis here, right? So the mean of the adjectives is the same as the grand mean, okay? Similarly, the next hypothesis could be that the mean of the nouns is the same as the grand mean, right? And here we are specifying the three levels of the factors for the benefit of the hyper package. So the hyper package now knows that there are three levels in this factor, and these are the two hypotheses that one wants to test. So when I save this object, the hyper object, as HCSum, and I look at the content of HCSum, what you'll see is the two null hypotheses laid out. And the names of these hypotheses are coming from these names that we specify, okay? And what this 2 times adjective minus noun minus verb divided by 3, the whole thing divided by 3, all that it's doing is that it's just rearranging all the terms here on one side of the equation, leaving 0 on the other side, because that's what the null hypothesis is. So this statement that the mean of the adjectives is equal to the grand mean is the same as 0 is equal to 2 times adjective minus noun minus verb, the whole thing divided by 3. You can just do the algebra and see why this turns out to be the case. So whatever the singular condition is, like the adjective or the nouns here, this will end up with a weight of 2, and these guys will end up with a weight of -1 each, and the whole thing is scaled by the 3 here, okay? So this is just a restatement of the null hypothesis, and just prints out the call that you had given, and is just rewriting this statement by opening the brackets, so dividing each term by 1/3, right? Or multiplying each term by 1/3, sorry. Same thing here. So right, so the two hypotheses are now laid out in terms of the weights for each of the levels, right? So adjectives get a weight of -2 of 2/3 here, and nouns get a weight of 2/3 in the second hypothesis, and the other terms get a weight of 1/3. So these are the weights. These you can see now for the weights for the two hypotheses, and hyper also prints out the corresponding contrast matrix for you, right? So the way to interpret the contrast matrix is that whatever is -1 is not involved in the comparison as such, like is not one of the comparisons of interest. The first comparison, B1, is comparing adjectives, which is coded 1, with the grand mean, and the second comparison is comparing nouns, which is coded 1, is compared with the nouns are compared with the grand mean. So what the hyper package does for you is that it allows you to write out the null hypotheses that you're interested in testing, and it prints out for you the corresponding weights and the contrast codings that you need to put into the model, okay? Right, so these are the contrasts that you will need to put into your model now. So what you can do is, in the column df contrasts to $f, this is the factor with the 3 levels, adjectives, nouns, and verbs. You're plugging in the result of this HCSum object by passing it through the contrast hypothesis. So the contrast hypothesis function is extracting the contrast matrix, plugging it into this columns contrast coding, just like the contra dot sum and contra dot treatment built-in functions in Arduino, right? Okay, so let's take a look at the flexibility, of this approach. So let's take another standard example. Let's say you have 4 conditions, right? So what are your options there out of the box? In R, one option is to do a treatment contrast. The treatment contrast takes a baseline condition, and that is the estimate of the intercept, and then all the other conditions will be the difference between the baseline condition and each of the other conditions. So that's what a treatment contrast looks like. Now, if you were to create an empty hyperobject and put in the treatment contrast, this thing that I just showed you, into the hyperobject using the CMAT function. So you're telling the H object that the contrast matrix should be the same as the contra treatment function's output, this thing here. This is just for illustration, okay? So what will happen is you'll get a warning which says that the contrast matrix that you're assigning to this hyperobject does not appear to have an intercept column, which it doesn't, right? So you see that we don't have a 1 1 1 1, or is it yeah, right? We don't have the intercept column here. So that's what it's complaining about here. And then it says if it's intentional, if this is intentional, you can ignore this warning or suppress it by explicitly calling the CMAT function. Where was the CMAT function? Yeah, this CMAT function, right? You can add underscore intercept equal to false there, right? And then give the contra treatment that then the warning should disappear, at least theoretically. So anyway, but what does the hyperobject now contain? Now that you've put in these 3 null hypotheses, right? I'm comparing 2 with the baseline, 3 with the baseline, 4 with the baseline. So what it surprisingly produces is, because the intercept is not there, right? Its first hypothesis is that the second level's mean is 0. That's not what we want. What we actually want in a treatment contrast is that the difference between the second level's mean and the baseline level's mean is 0, right? That's what we want, and that's not what we are getting here. So these are different hypotheses that you're testing now. So we are not going to use that, right? So all this is output now showing you what hypotheses you're testing. So the point is, if you make a mistake like this, you can always check what the hypotheses are in the hyperobject that actually correspond to the contrast coding that you're using. And if they don't correspond to your hypotheses, then you've made a mistake. Okay? So this contrast matrix is what we plugged in, and the hypotheses that we got back don't make any sense for us actually. Okay. So what we're going to say is now we're going to redo this in the hyperobject, empty hyperobject. We're going to specify add intercept equal to true in the CMAT function, and then add the contra dot treatment codings. And when you do that, the output of the contents of the H object will now contain 4 hypotheses, as they should. One is the intercept, that the baseline conditions mean is 0. That's the null hypothesis. And then the difference between the x2 and x1, x3 and x1, x4 and x1, these are the correct null hypotheses now for the treatment contrast. So now we've got the correct hypothesis set up. And if you look at the contrast codings, what you will see is that it looks a little bit different, right? So, sorry, this is the weight, the contrast, the hypothesis matrix. So this is the weights, right? But if you look at the contrast coding, you'll see that there is one column here containing ones, right? So now the intercept is included. And these are the correct contrasts that you will be putting in, right? And the 4 hypotheses being tested, I've already explained. So the point of this section was to just show you that how you can, take one of the built-in contrasts, plug it into the hyper object using the CMAT function, but you have to say add underscore intercept equal to true. Otherwise, what's going to happen is that you're going to end up with the wrong hypothesis. Okay, so just be careful about that. Sorry, I have allergies. Okay, so I mean, in a way, what I just did is kind of crazy, because why would I use a contra dot treatment contrast coding and plug it into a hyper object? So the whole point of the hyper object is that you can define your own hypotheses, right? But very often our hypotheses actually do correspond to the standard tests, so it's not completely insane, I guess. All right, so the next example is the Helmut contrast. And the Helmut contrast basically allows you to do the following. So if you have four conditions, right? So let's say 1, 2, 3, and 4 are the four levels of the condition. You can compare levels 1 and 2, ignoring the other two conditions. Sorry. And you can compare the mean of the first two conditions, with the third condition. And you can compare the mean of the first three conditions with the last condition. So it's a kind of stepwise comparison, of sets of conditions here, right? So what this kind of contrast really does is it asks the first hypothesis it's testing is, are the first two conditions different from each other or not? Then the next hypothesis is the average of the first two conditions different from the third condition? And the last one is the average of the first three conditions different from the fourth condition's mean?
Recording in progress.
So how do we set up such a contrast? Well, first I'll use the Helmut contrasts here that are built in and do the same thing that I did earlier, which is I create an empty hyperobject and then plug into the hyperobject using the CMAT function, the contra.helmut coding for four conditions. I'm again going to get the same warning and as before, but the three null hypotheses that we are testing will show up correctly now. So they are showing mu2 minus mu1 is equal to 0. So the average of these two is equal to 0. And then the other hypotheses are exactly what I said earlier, so I won't repeat that. Okay. So what you get as an output in the weights matrix. So this is just algebra now, because we're just rewriting the comparisons, between the sets of means that we're interested in comparing. What is interesting to look at is the contrast matrix here, right? So this shows us exactly the same contrasts that I'd shown you here. These are identical now, okay? Of course, that's what we had put in, so this should not be a surprise. But now if you put in add intercept equal to true, the warning will go away and the comparisons will look like this, okay? There will be an additional hypothesis that is set up that is for the intercept. And that hypothesis will be testing whether the grand mean is different from 0 or not. So if you remember in linear models and linear mixed models, of course, we always need to have the intercept. We never remove the intercept, even though it doesn't have any interesting hypothesis test for us to test. That intercept is just there for technical reasons, which you can find the answers to if you look at any kind of textbook on linear modeling. It's not a topic we need to go into. But what the three hypotheses, that are of crucial interest to us in the Helmholtz contrast, they are all, represented correctly, just like in the example I showed you a few minutes ago without the intercept, right? So they're all set up correctly. And now if you look at the contrast matrix again, what you will notice is there's the intercept, the grand mean, and then the three contrasts. So these are the same contrasts in the contra dot Helmholtz contrast coding, right? So all I wanted to show is that add underscore intercept equal to true is kind of important for specifying the four hypotheses that are tested, even though only the three slopes are of interest, right? Okay. So so we've looked at Helmholtz contrasts, and before that we looked at the three condition case, right? So now I'm going to talk about a four condition case where you have sliding or repeated differences or successive differences contrast. So in the mass package, there is a contra.sdiff function that for n conditions, so n is 4 here, it sets up the following comparison. If there are four conditions, it will compare the second to the first condition, the third to the second condition, and the fourth to the third condition. So you can see the names of the comparisons here, and there's contrast matrix here that is not at all intuitive. Like if I just eyeball this contrast matrix, I wouldn't really know what comparisons are being done. So let's try this out with hyper. With a hyper object, we create an empty, with a hyper function, we create an empty hyper object, H, and using CMAT again, we plug in the contra SDiff, same warning as before because of the intercept issue. And you'll notice that now the comparisons are what we want. X2 minus X1 is equal to 0, X3 minus X2 is equal to 0, and X4 minus X3 is equal to 0. Intercepts missing, right? So if you look at the weights matrix and the contrast matrix, you'll see that the contrast matrix is again not at all obvious, what it actually means. It's the same as the one we saw earlier. And now again, if you add the intercept, right, same situation, but you've added the intercept, now you get four hypotheses. The first one is again that the grand mean is equal to 0, just like in the Helmholtz contrast, right? And so if you look at now the hypothesis, the contrast matrix, sorry, you'll see this new column here, and then again the same weights, right? So the point is the weights don't actually change, the contrast matrix doesn't change for the slopes, but you do need to account for the intercept always. And the practical relevance of this is that when we are defining linear models and doing these kinds of comparisons, we, or at least I and many other people, what we do is that we define these columns, each column corresponding to one contrast by hand, so to speak. And I'll show you in the end what I mean. I don't plug in the contra dot treatment or contra dot Helmholtz or whatever into the factor level coding, inside the data frame. And so there it's important to see what the contrast coding is going to look like for the four conditions, right? And there will always be this first column containing ones, right? And this is of course what the design matrix will look like too, right? In the model matrix. That will be the form of this model matrix. Okay, so the last topic is contrast coding for multifactorial designs. So you can very often end up in a situation where you have a 2x2 design or a 2x2x2 design or something. And so or a 2 by 3 design or 3 by 2 design or whatever. So in those situations, you can set up an ANOVA style coding. I'm only going to talk about 2 by 2 designs, so something like this here. There are two factors A and B. Each factor has two levels, and so you could have the two B levels inside. Oh, sorry, the two A levels for factor level B equal to B1. We have no difference between A1 and A2, and in level B2 for the B factor we have a big difference between A1 and A2, right? So this would be a classic situation where you got an interaction between the two conditions, right? And we would, if we were to check for the main effect of um, factor A, we would take the average of these, and look for a difference between those two averages. Same thing for the factor B, right? We would do that for the two levels inside factor B of factor A to figure out the main effect of factor B, right? So this is the setup. I've got factor A, factor B with two levels each, and this is also simulated data, and we could do an omnibus ANOVA, you know, where we take the data frame, define the dependent variable, say what the between subjects factors are. Notice in this chapter we are only talking about between subjects, but the logic holds for within subjects too, right? So in an omnibus ANOVA, we define the two factors, and then if you look at the output of the ANOVA using the get ANOVA table function, you would see that you have a main effect of A and B and an interaction. We know that from how? From these p-values, right? That's what we know then. And the f-scores, of course, right? So this kind of 2 by 2 ANOVA comparison, you know, that involves two main effects and an interaction, one has to use some contrast in the linear model or the linear mixed model. The situation is different when you have more than two levels, okay? But let's just talk about the two levels here. So if I set up my the A levels, right, using contra.sum for with two specification that there are two levels here, then I would have some contrast for A, some contrast for B, right? That would be a standard way to proceed. And if you set up the analysis, these are the main effects: A, main effect of A, main effect of B, and the interaction. This syntax is an abbreviation, which is equivalent to A plus B plus A colon B. Okay. So you look at the output of the linear model, and you'll see that the two main effects of A and B and the interaction are shown here. Right. So one thing I want you to notice is that the p-values of the linear model output and of the ANOVA are the same. Not only that, you can check this yourself. These f-scores, these three f-scores, they are the square of the corresponding t-values here. Yeah, these t-values. These t-values, if you square them, you get the ANOVA scores, because f is equal to t squared. So this you'll find in any stats textbook, right? The proof of that. All right, so you can extract the t values and look at those, and so then you can draw your conclusions. And if you square them, oh, I did that already, I forgot. And if you square them, you get exactly the f scores. okay, of the ANOVA, right? So anyway, you could do this in a Bayesian way, of course, but that's just the same thing as the standard linear model. There's nothing special going on here in Bayes. So uh, so what we are going to do now is write out the hypotheses that we are testing. So we could be testing whether the mean of F1 and F2, the mean of these two conditions is different from the mean of F3 and F4, right? So this would be one hypothesis. The other one would be the mean of F1 and F3 is it different from the mean of F2 and F4. That's the other hypothesis. And the last one is the interaction, which is asking, it's asking the question, is the difference between these two conditions in the B1 level of the B factor different from the difference between these two conditions, these two means in the B2 factor level. So is the difference of differences this difference minus this difference, is it different from 0? That's the interaction, right? And so that's what this comparison is doing here, right? So these weights look a bit puzzling, but they're actually not, because literally what we are writing out is the difference between F1 minus F2. Oh, sorry. Let me see again. F1 minus F3 is it different from the difference between F2 and F4. And if you put all those terms on one side and 0 on the other side, you will see that you'll get these weights. You will get pluses and minuses corresponding to this pattern here. If you get the pluses and minuses with the opposite values to the ones you're seeing here, just move them to the other side and move 0 to the other side, right? And you'll get the correct numbers. And so this one, dividing by 4, you know, if each of the coefficients in the null hypothesis are 1, you can divide both sides by anything. You know, you can divide by 4, you can divide by 16. So here we are just rescaling the factor comparisons by the number of factors that we have, right? That's all it is. And you'll see that in a moment. You'll see more about that in a moment. So in any case, these are scaled values. The denominators, the 4s there, are there because there are 4 conditions. We're just rescaling the levels here, right? But you can see that the main effect of A is this condition is paired up as +1 and these are -1 So we are asking for a difference between F1 and F2, the mean of F1 and F2 against the mean of F3 and F4 and so on, right? So if you invert this matrix, okay, so this matrix contains these null hypotheses. You invert this matrix using the generalized inverse, you will get the +1s and -1s that correspond to the omnibus ANOVA, okay? So if you plug the inverted matrix, the contrast matrix, right, into the F column and run the model, linear model, what do we get as an output? We get the same comparisons that we got earlier. You can go and check that. when we were using, the um, what were we doing? Sorry, here, right? This is the Bayesian model. Yeah. So what we had done here is that um, we had set up the sum contrast for level A, sum contrast for level B, and then just multiplied A with B to get the interaction, right? A plus B plus A colon B, right? And what we got as estimates here are exactly the estimates that we are getting now, having done it through the first defining the hypotheses, getting the hypothesis matrix, converting that through a generalized inverse to a contrast matrix, looking at the contrast matrix, plugging in the contrast matrix into the data frame, and then doing the linear model. Get exactly the same numbers, okay? And the same everything, right? T values, etc. Same thing with BRM, you could do the same thing, so I don't really need to discuss that. Of course, you'll see that some numbers are slightly different, okay? So it's not -5, it's not exactly -10, but these are just numerical problems that you have with, multiplication and the use of MCMC or Hamiltonian Monte Carlo in Bayes. So you're going to find slight differences between the linear model and the Bayesian model, but basically there are no important differences there. The contrast coding works exactly the same in the frequentist and Bayesian setting, in the linear modeling multiple regression setting, and the Bayesian BRM, multiple regression setting. It's all the same. So it's not specific to Bayes or frequentist or anything. So we can set up the, let's try setting up the comparisons using the hyper package now, right? So in the hyper package, we set up an object, create an object first called HA times B, which looks at the main effects and interactions. And the important difference now is that what's useful about the hyper package is that you are starting by explicitly writing out your hypothesis tests. That's the usefulness of it. You can be very explicit, and the advantage of that is this is, of course, just a standard omnibus ANOVA. I mean, it's not a big deal, but the usefulness of it is when you are wanting to define custom contrast codings. That's when the hyper object becomes, the hyper package becomes really useful, right? So we are defining a hypothesis, same situation as before. We get the hypothesis matrix, and then we get the contrast matrix, and you'll notice that the contrast matrix now corresponds to the sum coding, contrast sum coding that I've been using throughout this course, um, in my comparisons of pairs of conditions, So what we are doing now is we are asking whether the average of F1 and F2 is different from the average of F3 and F4. It's the main effect of A. Same thing, everything else is the same, right, as before. Main effects and interactions. So I could now use the contra hypothesis function in hyper to plug in the contrast matrix, this matrix here, into the F object, and then I fit the model, and lo and behold, I get the same numbers again. Right, so I'm getting everything back, except there might be a difference here. These numbers are twice as large as the preceding models that I had fit. Very mysterious, right? For -5, 10, -10, and 5. And what do I get now? -10, -20, and 20. So what's going on? -5, -10, 5, -10, -20, 20. So this one is 4 times larger. This one is twice in the absolute magnitude, and this is twice the absolute magnitude. What's the deal with that? That has to do with the fact that my contrast coding has been rescaled here. Right? So I keep fitting the BRMS model here. Is it true? Yeah. So it's the same thing. Okay. Not interesting. So the estimates now have main effects that have double the size, and the interaction is like 4 times. The reason this is a more useful way to do the main effects and interaction is that the main effects and interaction now literally represent the effect size that is of theoretical interest to us. The slopes now actually represent the effect size. If we had done +1, -1 coding, we would end up with half the magnitudes in the main effects, and that that would not actually reflect the effect of interest, right? So that can cause a lot of confusion in the Bayesian setting because of the specification of priors, right? So you need to have your slopes represent the effect of interest. And the contrast coding is very important for determining that you have the correct comparisons and on the correct scale. So that's why scaling is so important here. Okay. So the best approach in this kind of main effects and interaction setting is to use +half, -half coding. So you should never use anything else. And that's because you can now specify a prior to reflect the actual difference of interest that you have. Okay. So there's a practical example of this. Okay. So there was a 2x2 design that we wanted to replicate. So there's a paper that we replicated, and the original paper was this one here. So in this original paper by Tabor et al., they had reported the effect size of the comparison of interest. The details don't matter. They're not interesting for us, right? What's interesting is that the original researchers reported a 73 millisecond difference with a 95% credible interval, which allows me now to define a prior that is informative, right, with mean 73 and difference and standard deviation equal to 132 minus 16, the whole thing divided by 4, because the width of the credible interval is 4 times the standard deviation. And so that gives me a basis for defining an informative directional prior for the effect of interest when trying to replicate the result, right? This kind of directional replication prior is useful for something called replication-based factor analysis. So you can read this paper from Wagenmacher's lab about why that's a useful thing to do, or why that could be a useful thing to do, right? So the main point I'm trying to make is that you want to define your contrast to reflect the actual effect size of interest, not half the effect size or whatever, right? With the +1, -1 coding. Often, in the frequentist framework, people are only interested in knowing whether the effect was significant or not. So if you ask an experienced researcher, you say an experienced researcher has been working on object and subject relatives for like 50 years. If you ask them what's the range of the effect sizes in object and subject relative clause differences, most of them will not be able to tell you that because they never paid attention to it. A few will, of course, know, right? They will have thought about it. But most will not have any idea, because what they will do is they will do a voting methodology. They'll say, oh, of the 50 studies that exist, 25 or 28 or 30 of them show a significant effect and others show a non-significant effect. They can't tell you what the magnitude of the effect is, right? And that's because in the frequentist paradigm, the focus is on the p-value, right? The significance or non-significance. In the Bayesian setting, we are really interested in the effect size estimate and its uncertainty. Why? Because in future studies, we want to use that information, right, as an informative prior. Whether it's a directional prior or not, that's a separate matter. Okay, so one last point is how to set up the contrast codings. Once you've set up your, you know, once you've figured out what the contrast matrix needs to look like, you can either plug in the contrast matrix into your column, containing the factor levels. That's one way, but that's not how I do it. What I do is, if I have two main effects in an interaction, I will create three columns: one for the main effects, one for the two for the main effects, and one for the interaction. And I will create the columns myself in the data frame instead of plugging in some contrast coding into the factor column. So if else can be used to define the contrast. So something like this, for the A and B conditions, I could say if the factor levels contain F1 or F2 coded as -1, otherwise +1. Of course, I just got done saying that you should use +½ and -½, but now again I'm using +1 -1. It's just for illustration. Okay, so don't take this to heart. Same thing for B. I could do +½ -½ or +1 -1 for the coding. So this is something I often do when I have a simple 2x2 design, right? And then for the interaction, I would just multiply those two vectors. And so I would have three columns ready to go to plug into the linear model or linear mixed model, right? So I would use, of course, +½ -½ and that's what I've done here. And then again, I would multiply the A and B vectors to get the interaction. And notice, of course, that the coding will be 1/4 minus 1/4. Okay, so half times half becomes 1/4, right? So that's how in a 2x2 design you could easily set up the contrast coding as new columns using the if else command. But if you have a 2x2 design, this becomes very, very cumbersome. This becomes very error prone and dangerous. So I use a different method there. When it's more complicated, I use the merge command in the following way. So suppose I have a 2x2, I'll just use a 2x2 design as an example. So suppose I have two factors, distance and predictability, which I'm calling predictability here just for convenience. Distance has two levels, short and long. Predictability has two levels, predictable and unpredictable. Okay, so it's standard 2x2 design. So here, my goal is to create one column for the main effect of distance, another column for the main effect of predictability, and a third column for the interaction. I mean, actually I can't. Oh, I could plug in, some factor coding here and here, then create the interaction. I could do that, but I prefer to create the three columns. Okay, so here's how I would do it. I would first create a contrast coding matrix. So let me just do this. Okay, let me see if this works in R. Do I have RStudio open? Wow, this must be the first time in the history of my existence that I don't have RStudio open. Let's open it. Oh, that's because the computer updated recently, so that's why. It shut down RStudio. So what I have is, I'll show you what I have. Contrast underscore coding. What I've created now is a data frame that has a column which is the same name as in the original data frame containing the real data, and a second column containing the second factor. So these are the two factors with their levels. but there's only 4 rows, right? I'm just putting in distance short or long, and predictability, predictable and unpredictable. Fully crossed. You see this? This is fully crossed design. Each combination of each factor level is represented here in these 4 rows. And then I set up the main effect of distance, the main effect of predictability in the following way. The main effect of distance is the average of these two conditions, these two levels, with the average of these two levels. So plus 0.5 for the first two, minus 0.5 for the next two. And similarly for predictability, first and third minus second and fourth, right? That's much more convenient when you have more than two factors, right? So like a 2 by 2 by 2 design or something. So now what I would do is once I've created this 4-row matrix or data frame, I would use the merge function to merge the actual data frame with my 4-row data frame. And what I'm doing is in the first data frame, which contains the full data, this is what by.x refers to. I'm asking the merge function to use the distance and predictability columns as the reference for merging the two data frames. And similarly for y in the second data frame, by.y is referring to this data frame. I'm asking merge to use distance and predictability to use those columns as a reference for merging. So what this merge function does is it looks up the full data frame, looks up my contrast coding data frame, and whenever the rows of distance and of predictability match, it merges those two. So that what will happen is that all this, oh sorry, here is it. These columns will be added correctly into the data frame. Okay. So that's what I've done here with the merge function. Got a new object called dat. If I look at the contents of the original data frame, I have 1512 rows, and after merging in the dat object, I also have the same number of rows, but 2 new columns. See that? 5 here and 7 here. If I look at the dat frame, I get those 2 columns there. Okay, that's much faster than writing the if-else commands, which are pretty tedious. And then the interaction, you can just add one more column by just multiplying these two guys. So you get the interaction here, right? So we are back to where we started, right? With the 2 by 2 contrast coding. The very last topic I want to cover is the nested effects. So you know, the figure earlier is very useful for this. So what one often wants to know is, right, consider this situation here. If I want to know within the B1 factor level, so this solid line level, is there a difference between these two conditions? And within the B2 factor level, is there a difference between these two conditions? That's called a nested contrast. Okay, so you can compare those. Of course, you could also ask yourself, within the A1 factor level, are these two conditions different from each other? Within the A2 factor level, are these two conditions different from each other? That's also a nested contrast. It depends on what your question is, right? This is often a question of interest for researchers. So you can define your nested contrast very easily. Right, so this is the section for the nested contrast. And so what we're going to do is we're going to set up the two nested contrasts under the level B1. What are the two A levels? Are they different from each other? And under level B2, are the two factor levels of A different from each other? Now, because you have 4 conditions, you still have to have one more comparison. And that comparison is going to be whether the uh, um, whether you have a main effect of the B factor or not, right? Because what we are checking is under the two levels of B, do we have an effect of A separately, right? That's what the nested contrasts do. Like in B1, is there an effect of the two conditions, two levels of A? Under B2, is there a difference between the two levels of A? That's the comparison, that is the nested contrast. But in addition, whenever we are looking at the two levels of, let's say, the B factor here, then we would want to look at the main effect of B as well, okay? Which is the same thing that we just studied a few minutes ago. If I was looking at the opposite situation, under A1, is there a difference between the two B levels? Under A2, is there a difference between the two B levels? Then I would put in a main effect of factor A as my third comparison. Because for 4 conditions, you always need a 4 minus 1, 3 comparisons. Okay, that would be a full specification. So these are my hypotheses. Okay, I set up my hypotheses, invert the matrix, I get my contrast matrix. Okay, so now I'm ready to roll, right? I've got my sum contrasts here for the nested conditions, and then the main effect here, just like before. Nothing special going on, except that I'm looking inside each level of the B factor. Okay, so I plug in the inverted contrast matrix into the F column, and then once I fit the model, I get the main effect of B here, and then the effect of A inside B1, the effect of A inside B2, right? That's how you would deal with nested contrasts. The nested contrast can also be implemented in a hyper, of course. So you set up your main effect of B in this case, right? Then the two nested comparisons, that will give you the contrast matrix again, which is what we just did by hand, by inverting the hypothesis matrix. And then you can just use that using the contra.hypothesis function. You plug in the nested contrast coding from the hyper object, so it extracts this. So it extracts this matrix and plugs it into F, and then you've got your appropriate comparisons, right? So that's the story with nested contrast coding. And this is just an example of the reverse question, right? So if I want to look at the inside A1, if I want to look at the effect of B, inside A2, if I want to look at the effect of B, the levels of B, so I can do that too. So this is just reversing everything, right? But it's just the same, exactly the same setup. Okay? Which comparisons you would do depends on your research question. So that I'm just showing you in abstract how this would be done. Okay. So I won't show you this because it's really all straightforward. It's just more of the same, right? Okay, so that's the whole gigantic contrast coding chapters. Chapters 6 and 7 of the book. I will probably take 2 lectures to cover this material. And I'll give you plenty of practice with these.